property which we will discuss today is hardness. We have discussed it. What is hardness, right? We perform a test also in the lab, the hardness test. So hardness is actually whenever you have a material, when you can say that this material is hard, right? So the material will be hard when you try to deform the material in the form of like abrasion, indentation, scratching. If you want to cut it, if you want to shape into some different desired shape, let's say you want to make something from the material, and if it is easy to convert the material into that shape, it means it is not hard. But if it is difficult to convert it into that shape, it means that the material is hard. If it is easy to scratch a material easily, it means it is not hard material. But if you cannot scratch a material, it means it is hard material. If you can make a dent, let's say you have the indenter and you want to make a dent in the material, you know dent, right? So that is, if it is easy to dent, it is not hard material. And if it is not easy, it is hard material. So hardness is this property of metal, right? So hardness is what? It is the measure of the material resistance to localize the plastic deformation. Localized plastic deformation, I told you, we want to scratch. So scratching we do at one part of the material. It is localized at one part, right? If we want to make a dent, so dent is also a plastic deformation, and we also wanted to make it in one part of the material. If you want to scratch the mobile screen, so if you are scratching here, this is localized. It is not, you are not applying something on the whole material. Like the tensile testing, we are applying the force on the whole material, right? Here we are not applying on the whole material. This is localized plastic deformation. So early hardness tests were based on natural mineral with a scale constructed solely on the ability of one material to scratch another that was softer. So in the previous days, when there was no technological equipment and all these equipment today what we are using, they check the hardness of the material comparatively to other material. They take one material and try to scratch another material. Let's say this material can scratch this material, so means this material is hard and this material is soft. That was a qualitative test. And what they have done, they make a range or a scale known as Mohs scale, and this Mohs scale was ranged from 1 and 10. So 1 was used for the most soft material, and that soft material is telic, and this is telic material. I forgot the name telic, right? So this TALC, this is the material which is the soft material in the available in our earth. And 10 was used for the diamond. You see, we have diamond, which is the hardest known material on the earth. So if we gave a value 10, so means it is the hardest, the diamond material. If we gave a value 1, it is TALC, telic material. This material, right? Or if something is, let's say, we call it something, let's say the value is 8, means the material is hard, right? But not hard like the diamond, but close to the diamond, you can say. If we have the value, let's say 2, so means the material is soft. So that qualitative test was done previously. Then later on, the quantitative hardness techniques have been developed over the years, right? So a small indenter is forced into the surface of the material to be tested, what we have done in the lab, right? Under a controlled condition of load and the rate of application. So now what we are doing, now we have an indenter, we force the indenter into a material to one point on the material, right? With a controlled load, right? And then we measure the depth or the size of the indentation, the diameter of the indentation depends on this, and which tell us the hardness number. And from the hardness number, we can see that whether the material is hard or the material is soft. So now we are doing this quantitative testing. Previously, the quantitative tests were not available, so there was a scale from 1 to 10. Clear? This is the hardness. Now hardness can be defined further. I already told you about hardness, like we have the indentation hardness. If we want to make a dent in the material, or the material will be resistant to the indentation. That is indentation hardness. If the material is resistant to scratch, so means the scratch hardness is there in the material. Rebound hardness is there. Micro hardness there. At micro level, what will happen to the material? So all these types of hardness are there. Now, the indentation hardness, you see the resistance offered by the metal to indentation. This is the commonly used test. Mostly the hardness test or the hardness test equipment are available are based on the indentation hardness. So in this what we do, as I told you in the lab, we take an indenter, which is the hard material, usually most of the cases it is diamond, and that is forced into the surface of the metal. And then we see how much depth is there, how much indent is there. So what is the diameter of the indent, or what is the depth of the indent? We measure that, and from that we have different formulas for different tests, or we have different tables that are also given in some of the cases, and we compare it, the value of the diameter or the value of the depth of the indentation, and we can find the hardness number. Now, why we are doing the hardness test, right? Now, the hardness test is performed frequently as compared to other tests, and there are several reasons for this, right? The reason are, the first thing is the hardness test is inexpensive, right? And the hardness test does not require any special specimen. You can take any specimen, put it in the machine, and make a dent, right? So the specimen which I showed you was just a disc material, right? It doesn't mean we have to fix that the geometry of the specimen, that always we will use that disc type. No, you can use any specimen. Take a rod, take a sheet, whatever you want, put it in the machine and make a dent, and you can find the hardness, right? So no sample or specimen preparation is there. So that's why it is most common, and the testing apparatus is relatively inexpensive. So we can use, everyone can afford it. So to test the material. Now the second thing is the test is non-destructive. If you look into the macro level, we don't destroy the material. When we don't deform the material up till that level. There is a deformation at micro level, but usually we don't care about the micro level. But in some application, it can be destructive. This is comparative thing. We cannot say at all that this is non-destructive at all. No, for some people it will be destructive. But usually, as a mechanical engineer, what we are dealing with, you people will be dealing with the macro thing, right? Not at the micro. So that's why we are saying this is non-destructive. But yes, keep it in mind, this thing is relative thing. The specimen is neither fractured nor excessively deformed. As you see here, excessively deformed. It means there is deformation, but that deformation is very, very small, right? Micro level, like you can say 70 micrometer or 0.7 millimeter, or let's say 0.5 millimeter, 1 millimeter maximum, 2 millimeter. So there is a little bit deformation. So small indentation is the only deformation in this test, right? We don't have any other deformation. That only small indentation is there. So other mechanical properties often may be estimated from the hardness data, such as the tensile strength and all these things. So that's why we use the hardness test. This is the reason why we use the hardness test. Now, how many types of tests are available for hardness? We have three different types: Braniel hardness test, Rockwell hardness test, and Weaker hardness test. We will discuss all these in detail in today's class, right? Now, all these tests, why there are three different types of tests? They are different in different criteria, like shape of the indentation can be different, size of the indenter will be different, even the shape of the indenter is different. Some cases we use ball, some cases we use cone, some cases diamond, right? The applied load can be different. And why we want this different thing? Sometimes we cannot apply too much load on a material. That's why we need less load. So maybe too much load will destroy the material permanently. So that's why we have different tests also. So for less load, we have test, and for some material we use the less applied load test. And for some material we use the size of the indenter bigger. For some material we can use the size of the indenter smaller. It depends. So method of measuring diameter is different. Some cases we measure the diameter of the dent. Some cases we measure the depth of the dent. Right? How we measure? In some cases we take two diameter and then we take average. In some cases we don't take it. And depth of the impression is also measured. Now, once you have the hardness value, usually what we have done in the lab, I told you that this value will come on this force. So if you, let's say you have the same material and you apply, let's say 1 Newton force on that, you will have one hardness value. But you can say that if you apply, let's say 100 Newton on the same material, so the dent will be more. Then you will have different hardness value, right? But this you have to keep it in mind. Whatever value of hardness you want to find, right? You have to write that this value was found at this much force. If you don't write at this much force, then this is the insufficient data. Like if I have the same material, let's say the aluminium, I apply a force on the aluminium, let's say 2 Newton. And the same material I test with the same machine and I apply a force 10 Newton or 20 Newton. And the hardness value or the hardness number we are measuring from the, let's say, the diameter of the dent. So of course the 20 Newton force will create bigger diameter. So the hardness value will be different here as compared to the hardness value found with 2 Newton force. So whenever you find or whenever somebody tell you that this is the hardness value of the material, right, there will be the force will be written. If the force is not written, so that you cannot say that this is the accurate data. Right? Wherever you have question, ask me, guys. So now we have the first one, the Braniel hardness test, right? We discussed this, but just quickly we are doing. In today's class, most of the things we discussed in the lab, right? But this is just a repetition. Now, in the brachial hardness test, similar to the radial hardness test, we will study the radial hardness test. A spherical indenter is forced into the surface of the metal, right, to be tested. Whatever material we want to test, we force a spherical, or you can say a ball, indenter, and it is forced into the surface of the metal. Now, the diameter of the hardened steel or tungsten carbide indenter is whatever indenter is used, usually it is tungsten carbide, right? And that is 10 millimeter in diameter. So standard load range between 500 and 3000 kilogram. In 500 kilogram increments we can use. Like 500, then we can use 1000, 1000, 1500, 2000 kilogram, right? So in the lab test, I gave you a question like it was very much clear that the force is in kilogram or in two questions were there, and the force was in the Newton. So if it is Newton, you have to convert it into kilogram force. Kilogram force is the unit, right? So there was a simple unit conversion involved in that thing, but most of you have done it, but some of you did it wrong. Anyway, so during a test, the load is maintained constant for a specific time. And that specific time in the weaker hardness test, I told you that is the dwelling time, right? So between 10 to 15 seconds. And whatever we perform in the lab, we keep the load for 15 seconds. That was the dwelling time, right? So hardened material require greater applied load. So usually there is a range, right? From 500 kilogram to 3000 kilograms. So hardened material, we apply greater load. Why we apply greater load? With the small load, we cannot measure the dent. And it is very, very small, so then we cannot measure accurately. That's why we increase the load. So the brachial hardness number is a function of both the magnitude of the load and the diameter of the resultant indentation. So this table we will see in the coming slide. So this diameter is measured with a special low power microscope utilizing a scale that usually the microscope is connected to the machine. If it is not connected to the machine, we will have a separate microscope. You take the specimen, you apply the load, you make dent, and then you take the specimen and put it in the microscope and you measure the diameter of the indentation. So the measured diameter is then converted to appropriate hardness number using a chart. Only one scale is employed with this technique, right? So there is a chart. And that chart is, if you see, I have put one manual in the lab folder, in which the lab folder that was for Brooks. There's one machine, Brooks machine, the old machine we have. So, and that how the students were using the hardness number. They find the diameter, and then a chart is given. And in that chart, different values are given. If the diameter is, let's say, 0.5 millimeter, this will be the hardness value. If the diameter is this much, this will be the value. This much will be the value. So, a bigger table is given, bigger chart is given, and with that chart, we measure the brachial hardness number, right? And we also use the brachial hardness test formula. This is the formula which is used for the brachial hardness test. And you can see here, for iron and steel, we use the load 3000 kilogram, like the maximum. And for non-ferrous metal and alloys, we use 500 kilogram. So here the dwelling time is 30 seconds, here the dwelling time is 10 seconds. And the same shape is used in the indentation, and this is the machine used for the brachial hardness test. Right, with this formula later on we will solve one example, right? Here you see this is the applied load in kilogram, it is written kilogram, right? In diameter, and this is the diameter of the impression. Now the brachial hardness test, some more details here. The semi-automatic techniques for measuring brachial hardness tests are available. What they do, they make a dent and they tell you the diameter, somehow semi-automatic and even fully automatic. What you see in the weaker hardness test, that machine is fully, you can say, automatic. You put the specimen, and once you start, then you can find everything from the thing, but not that much fully automatic. You know, you have to press some button to see this one, right? But there are other machines as well. So these employ optical scanning system consisting of a digital camera mounted on a flexible probe, which allow positioning of the camera over the indentation. So this is just like how the machine will be. So the machine, the semi-automatic machine, they put the camera is just on a flexible probe, and you have to fix it at the point where you make the indentation, right? So the data from the camera is transferred to a computer that analyzes the indentation, determines its size, and then calculate the brachial hardness number. So whatever data from the camera you get, it will go to the computer, and in the computer, automatically it will calculate all these things. So for this technique, surface finish requirements are normally more stringent than the manual measurement. So for the automatic measurement, what we do, we polish or finish the surface, right? So surface finish is requirement. What does it mean? We have to polish it. As I showed you in the microscope, you saw the micro scratches. So what we do, we fix the specimen in the some region where there was less scratching. That's why we make a dent in that area. But once you are doing with the semi-automatic or automatic machine, the surface of the specimen should be properly polished, right? So because in that case, you are not deciding where to dent. The machine is deciding where to dent. So that's why we need more surface finish as compared to the manual measurement. So maximum specimen thickness as well as the indentation position relative to the specimen edge and minimum indentation spacing requirements are the same as for the Rockwell test. So for the maximum specimen thickness, the indentation position and minimum indentation spacing is required. So if you want to do indentation here, 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 with automatic very less, the spacing is required between the indentation. In addition, a well-defined indentation is required that necessitates a smooth flat surface in which the indentation is made, right? So a well-defined indentation means we have to apply enough force to make a proper dent so that the camera should read it properly and you will get the result. So this is the brachial hardness test and that's how we perform it. We have the Rockwell hardness, right? So Rockwell hardness test, this is the also mostly used test. This is fast and free from the personal error. Small size of indentation is made. So if you are worrying about the indentation, about the permanent deformation in the material, you don't want bigger size of the indentation, so you can use this test. The procedure, the things are similar to the brachial hardness test, and the depth of the impression is measured rather than the diameter of the impression, right? So here we take the depth of the indentation rather the diameter. Here you see for the Rockwell we use the hardened steel ball indenter, which will be the ball indenter, and we can also use the diamond cone indenter. It will be of this shape. So for this one we use the load up to 100 kg, and for this one we use the load up to 150 kg. So this load I found in some other in some slide I have put. Some people say this load is okay, and some are saying there is a different load value. But I think I have put that thing in one slide. I will show it to you. So these two types of indenter are used. Now the Rockwell hardness test constitute the most common method used to measure the hardness because they are so simple to perform, require no special skill, right? So we can do it. So all hardness tests, not only this one, they don't require any special skill, right? So several different scales may be utilized from possible combination of various indenter and different load, which permit the testing of virtually all metal alloys, right? As well as for some polymer. So here the indenter include a spherical and hardened steel ball having the diameter of this much, you see, different diameters are there. And a conical diamond indenter we can also use, which is used for the hardest material, right? So if the material is too hard, we use the diamond cone indenter. If the material is not that much hard, we can use with the ball or the spherical indenter. So with this system, a hardness number is determined by the difference in the depth of the penetration. So what we, as I told you before, we measure the depth of the indentation. So how much the indenter penetrates in the material, we measure that. And from there we find the hardness number. Right? Any confusion? There is more theory, but better you people study it, right? Yes, this I will explain, but this theory you have to study. Are you with me, guys? That's okay. Now here, what we do, we have two types of tests for the Rockwell, right? As I told you that there are different loads and different things are there, so we have two types of tests. Now we have not discussed these things in the lab, but here we are discussing. So on the basis of the magnitude of both major and minor load, there are two types of tests. One is the Rockwell and the other one is superficial Rockwell. So Rockwell, what we have in the Rockwell and what we have in the superficial Rockwell. For Rockwell, the minor load is 10 kg, whereas major load is, these three loads can be used, 60, 100 and 150 kg. Right? Each scale is represented by a letter of the alphabet. And then we have the superficial Rockwell. So for the superficial test, 3 kg is the minor load and 15, 30 and 45 kg is are the possible major load value. So in the superficial Rockwell test, we use less load, right, as compared to the Rockwell test. So these scales are identified by the 15, 30, 45 according to the load. Whatever load we are using, that will tell you that we have measured the Rockwell, the superficial Rockwell test, or we have performed the test using this scale. Scale means the 15 scale, 45 or whatever, and it will tell you the value. So superficial tests are frequently performed on a thin specimen, right? So because the load is less, so we do it on a thin specimen. And table 6.6b presents several superficial scales. So these scales are here, you see. So we have the Rockwell hardness scale and we have the superficial Rockwell hardness scale. So scale symbol is A, B, C, D, E, F, G. These are the scale symbol. This is the indenter and the load is written here, which load we want to use. Same for the superficial scale. You see the 15N, all these. And 30N, 45N, 15T. This is the scale. And we have the indenter is given here and the load is given here. Right? This N, this is just for the scale. Don't compare that 15. N means 15 Newton. It is not Newton, right? The load is kilogram, 15 kilogram. Here we have the scale ABC. Here we have just wrote 15N, 30N, right? 45N or something, the scale like this. So these are just the scale. So these two types of tests, we have the Rockwell hardness and the superficial Rockwell hardness scale. Now here you see we have different types of hardness technique are the machines are what we study. We have the brainial hardness. You see, we use the indenter 10 millimeter sphere or steel. Tungsten carbide is used, right? So you can see here the view, the shape of the indentation. The top view is here. The load is represented by the P, and we use this formula for the brainial hardness test. The weaker we are coming in the coming slide we will study, but here you see the Rockwell and superficial Rockwell test. So this is the two things, the cone-shaped indenter and the ball-shaped indenter are used, and the load is represented here by these things for the Rockwell and superficial Rockwell. Usually for the Rockwell and superficial Rockwell, the formula is not given, right? So there is one formula some people use at 0.2 into 10 raised to the power, minus E, that formula, but it is not common. 1 minute. It is 0.2 minus E raised to the power something. But this formula, nowhere you will find, right? So what they do, they will give you a table. And in the table, you find the diameter here, right? Or the depth here, and the table, they have given a lot of values for the hardness number. So whatever diameter you measure, then you compare in the table and you see that this is the hardness number. Then we have the no and weaker micro indentation hardness test. This is the one which we perform, right? So both are the same, the no and the weaker hardness test. The two hardness test technique are no and weaker, sometimes called the diamond pyramid test. This is also known as the diamond pyramid test. For each test, a very small diamond indenter having a pyramidal geometry is forced into the surface of the specimen, right? So this I already explained to you. We have a diamond indenter, small diamond indenter, and we will force it into the surface of the specimen. So the applied load is much smaller as compared to the Rockwell and Rangel. It is like from 1 to 1,000 gram. Here it is gram, right? Not kilogram. So the resulting impression is observed under the microscope. You can study this as I explain these things to you. What we do, the whole video you have, right? So we take a specimen, we put it in the machine, we apply a load in this range, right? A small diamond indenter is then forced with that load for some dwelling time, which the dwelling time we set was 15 seconds, and then we see there is a dent. Then with the small microscope, right, we see the size, the diameter of the pyramid indent. So we take two diameters in the x-axis and in the y-axis, and then we take average of the diameter. And then we put the diameter in the formula and find the hardness number, right? So this is the whole thing. We discussed it, but you have to read it. And here is a little bit schematic, which I explained you before. Here are two formulas. Like this formula is also used, and we have another one which I showed you in the video. So they are same. Don't you people are confused in this. Like if you have 1.8, take your calculator 1.854, and if you divide this with 9.8, like G, 9.8 meter per second square, so it will give you the other value, right, which we use in the other formula. So this comes from when, so you have the force and you want to convert it into mass. So F is equal to ma, right? So mass is equal to the force divided by acceleration. So if we have the force here in the Newton and we want to convert it into kilogram force, right? Then we have to divide the whole number, including the force, or if you divide before this only the constant number with 9.8, and whatever value you get, you multiply with the force in Newton, you will get the force in kilogram force, right? This kilogram force is a unit, like a not standard unit, but they are using. It will be in the kilogram. So the difference in the two formula is this one. Once you convert it from Newton to kilogram force. Here you see, in the book, this formula is used for the weaker micro hardness test, right? and we have the angle 136 degree between the opposite side, and we measure like D1 and D2 same way like this. So this is how we perform the weaker hardness test. Now some scales are available here for the conversion of hardness. So hardness number, once you have the hardness number with the NOF machine, with the Braniel, with the Rockwell B, Rockwell C, right? For different material, you see on this side we have different material. Diamond is the hardest material. You see here, this is the old scale. In the ancient time, they were using this scale. So we have the Mohs scale. I explained in the start. We have Mohs scale. In that scale, 1 is used for the soft material, the telic. You see here, this is 1. And here we have the diamond, which is the hardest material. So we scale it 10. All others are in between these two. You see here. So, and we have other materials here. Now, if you see here, the Braniel hardness number, so if you measure for diamond, it will be somewhere here in this range. If you measure for, you see, whatever quartz, it will be here. Now, you see the Rockwell B, we cannot use this one for diamond. You see? So, diamond is here. So, that's why we need the other specimen. That's why we have the other test. And from this scale, you can see for which material you will be using which specimen, which is which type of test. Or if you have one value for specific specimen in the knob and you need Braniel hardness, you can convert the value using this type of scale, right? So this scale is also given here. Now there is one another thing, the relation between the hardness and the tensile strength. You look here, we have the hardness values, or the hardness number, the Braniel hardness number, and we have the tensile strength. The tensile strength tells us how much the material is strong, right? Both the tensile strength and hardness are indicators of metal resistance to plastic deformation. This we discussed that the hardness is also a deformation, plastic deformation, but hardness is localized plastic deformation. We know that here we will deform, or here we will do the deformation. While in the tensile strength, or once we are doing the tensile test, in the start we don't know where the material will break. Right? So we apply the force on the whole material and then it deforms at some region. But in the tensile strength, we completely destroy the specimen, while in the what you call the hardness, we don't completely destroy the specimen. So there is a relation between the tensile strength and the hardness number. So they are roughly proportional. Now the tensile strength and the hardness number are roughly, you can say they are proportional. Proportional means that the hardness number is increasing, the tensile strength is also increasing for the specimen. So the same proportionality relationship does not hold for the metal as shown in the figure for the indicator of cast iron and brass. So we have here for cast iron, which is this one, we have brass and we have steel. So all these, you see, the hardness number is here on the x-axis, the tensile strength is here in the megapascal on the y-axis. Now, if we are increasing the Braniel hardness number from 100, we are going to 400. You see, here we have the tensile strength 500 megapascal, while here we have, let's say, 1500 megapascal. So there is a relationship, somehow proportional, right, for most of the material. But as a thumb rule, we use a formula, and that formula is that the tensile strength is equal to 3.45 multiplied by the hardness weight, the Braniel hardness number. You see, this is in the PSI, this was in megapascal, right? So in the megapascal, we just multiply 3.45 with the hardness value and we get the tensile strength in megapascal. So there is a relation between the tensile strength and the Braniel hardness number. Now here you can see for different material, the Braniel hardness number value is given in the table and the tensile strength is also given. So you see for 1040 carbon steel, we have the Braniel hardness number 235 and its tensile strength is 750 megapascal. So for these materials, somehow as we are increasing the Braniel hardness number here, it is not changing that much. You see 220, 250, 250. Here also the tensile strength is almost constant. You see, so it is not arranged in proper order, like from increasing to decreasing or decreasing to increasing. But you can still, you can see 235 we have 750, while for 160 or 40 Braniel hardness number we have 150 and 461. So there is a relation, but don't look into this table that they are arranged in some proper order. No, they are not arranged in the order, they are random. So this is like for different material, we have the hardness value and we have the tensile strength. Now here we have one example. You guys will solve it and let's see how you solve it. Look what is in the example. A Braniel hardness measurement is made on ductile iron. This is the iron, whatever iron we have, air quenched iron. using a 10 millimeter diameter sphere of tungsten carbide. So tungsten carbide diameter sphere indenter is used. A load of 3000 kilogram produces a 3.91 millimeter diameter impression. So the diameter of the impression is 3.91 millimeter. Calculate the Brazil hardness number of this alloy, right? For this alloy, which is the ductile iron, this 173 air quenched alloy, we have to measure calculate the Brazil hardness number. And you can see the correct units for the Brazil equation of table 6.9. This is like from the other book, but ignore this thing. This example I have to from other books, so table, leave it. But what you will do, you have the data, right? And you have the formula. So find it, you have it in the kilogram, the force. Now see how you will find. Look here. Where is the formula? Here. So this is the Brazil hardness formula, right? So you put everything here and you find it. Everyone please find and see what values you are getting. Once we find the Brazil hardness number, we have to look into this table. It is this table, right? We have to look into this table and see what is the tensile strength of the material in this table. So here we have the solution. The question was very much clear, right? You have to find the Brazil hardness number. The force is given, the diameter is given, everything is given. You have to just put it in the formula and you will get the Brazil hardness number, 240. And then from the table, if you look into the table here, 240 lies here, in between somewhere here. And for all the things in between, we have 800 megapascal. Right? So for 220 we have 800, for 250 we have 800, so means in between we also have 800. So then 800 is the tensile strength of the dead iron alloy. So this is how we solve the example. Now we have the creep, another property which we have also discussed, but I will quickly explain to you and then I will leave you for sleep. So with this we will finish the mechanical properties, right? Now what is creep? We discussed in the lab class in detail. Creep is a plastic deformation which occur over a constant load for usually for long period of time. So the tensile test alone cannot predict the behavior of structural material used at elevated temperature. Now, you remember the video for the tensile strength. At the end, I told you that we have this machine and we have furnaces. There were furnaces behind the machine, which we have not used, but there were. So when we use those furnaces, we test the material at high temperature. And as I told you, whenever we are using the boiler, the different what you call the steam engine component and all these, wherever there is a high temperature, the oven, right? So those components, we need to do the creep testing for those components, right? To see at high temperature and at constant load for a long period of time, what will happen to the specimen. So that's why we do the creep test, that at elevated temperature, we can not only find properties from the tensile test. So the strain induced in a typical metal bar loaded below its yield strength at room temperature can be calculated from Hooke's law. This is we know it, right? Repeating this experiment at high temperature, like T greater than 1/3 up to the one half times of the melting point. Now the temperature greater than the 1/3 to 1/2 times the melting point on an absolute temperature scale. And what we do the testing at that much temperature, then we see that at this temperature, what deformation will be there in the material, right? So for those types of testing, for those types of behavior of the material, to know how it will behave at that surrounding or at that environment, we have to do the creep test. Now this figure shows the creep testing thing. We have the specimen here, the specimen here. So look here, this is the constant load. Whatever we have done, we put here specimen and then we have a lever and here we apply the load, but it is the same. Even if you directly apply the load to the specimen. And within the surrounding of the specimen, you can use furnace, right, to give it a high temperature. We have done the experiment at room temperature, but usually it is not done at room temperature. You have to do it at high temperature, right, depending on the specimen or depending on the application of the material where you will use. So we have the specimen, we have the temperature environment, and then we apply a constant load to the specimen, and we see how much it will behave, how much deformation will be there. So creep can be defined as the plastic deformation occurring at high temperature under constant load over a long period of time. Now in the lab video, I have explained this again and again, that it is a constant load. Then in the lab test, I have given two questions. Same true question. That in the creep test, the load is increasing slowly and slowly. You people say true. Then another question I say, then the creep test, the load is decreasing slowly and slowly. And some guys make true for both. Now I don't know. Even if you are saying that it is increasing, okay. Then on the another question it should be decreasing. It should not be decreasing. Then another also it should be increasing, so the another should be false. But some brilliant minds they put both true. Even none of them was true. I explained this again, constant load, right? Even in the video when I was putting the load on the specimen, I told you that this load will not change. And you watch the video, in the whole video, did I change the load? No. Then you have done those types of things. Why? Because maybe in the video you are also sleeping. I don't know. But creep can be defined as a plastic permanent deformation. Keep this thing in mind. I will repeat the same question in the exam, maybe. Occurring at high temperature. So usually it is at high temperature under constant load over a long period of time. So these things are important for the creep test. Load should be constant, temperature should be high. How much high? Now 1/3 taking from 1/3 to 1/2 in this region, right? So let's say you have the melting point is here, and this is the half, this is the 1/3, and let's say this is the 0. So from here to here, in this region it should be, right? The temperature value should be from this region, if this is the melting point, right? And for long period of time we have to put it. It is not like for short. Why it takes long? Because the load is fixed, right? So then you cannot see the deformation immediately. It will take some time. So that is known as the creep, and that's how we perform the creep test, right? What about the specimen? Look, here for the creep test we use usually the specimen which has a uniform cross section, same like the tensile strength, right? And we have the shoulder also to fix it, and then we expose the uniform cross section to the what you can call to the load. So here again I have put that value. Now here you see these are the application in the boiler, the gas turbine, the jet engine, the oven, or any other application. We will use to see the behavior of the specimen. We can use the creep test. Now creep test is plastic deformation. You have to keep these things in mind, right? Question will be from within the slide. Don't, because you people don't focus. This is the thing. If tomorrow I put a question that creep is plastic or elastic, most of you will say it is elastic because you don't read the slide, you don't listen to. Why it is plastic? You have seen it in the experiment. What we have done, the material breaks even. And if you even don't break it, we see the plastic deformation. That the material cannot come back to its position. We don't leave it, right? Because we perform the experiment until it fracture or to its fracture. So usually these types of specimens are used. You see here, which we have done. And this is tensile specimen, right? Because you see we have a shoulder here, and we have a uniform cross-section area which is like in the gauge line. This I explained again and again that the creep test we use the specimen which is the tensile specimen. But then you put in the specimen photos that this cannot be used for the tensile test. Anyway, so the important thing, the creep curve, right? Look here. Now what happens once we are doing the test, right? I explained this before, but let me explain it again. We see the strain and we record the strain with time. So here on the y-axis we have the strain, we have the time here. Now what happens once we put the load on the specimen? In the start, the strain is increasing. There is too much deformation, right? There is a transient change in the strain, and that transient change, up to that much transient change, we call it primary stage of the creep curve. After some time, as I told you, once we see a little bit deformation in the material, then it is very difficult to see the deformation, and that deformation become a little bit, you can say, somehow constant for certain period of time, and that is known as secondary stage. Later on, once there is nicking started, and we see that the area is now starting reducing, then we see much more strain, and finally the material fracture at this point. So here the strain is too much, and this is known as the final stage, or we call the tertiary stage. Any name we give. So here what we do in the secondary stage, we have to find the slope, right? And that slope will give us the creep rate of the material. And the creep rate is like change in strain divided by change in time. You see here. So here you take two values of the strain and two values of the time. And that change in strain divided by change in time will give you the creep rate. And this creep rate we use it later on to for the material selection where there is a high temperature. right? So keep this thing in mind. Why we need the creep rate or the creep test once there is the tensile test. Excuse me. So we need it only for the what you say for the high temperature environment, right? So there's some specimen or some environment we put the specimen or the material and it is exposed to high temperature. So in the high temperature we have to do the test.